The question asked in class was, how do we find the average slope of y equals ax squared plus bx plus c between x equals h and x equals k? We approach the problem by first drawing a picture. Here we have the x-axis and y-axis, and we have x coordinates h and k. The value of the function at x equals h is just ah squared plus bh plus c, as indicated here. The value at x equals k, well, we plug k in for x and we get ak squared plus bk plus c. That's the value here. The slope, the average slope, is the rise divided by the run. The rise is from ah squared plus bh plus c to ak squared plus bk plus c, and that's going to be ak squared plus bk plus c minus the quantity ah squared plus bh plus c. The run is going to be from h to k, that's just k minus h, so the slope is what we see here. The altitude at x equals k minus the altitude at x equals h divided by k minus h. Now it turns out that we can do some simplification with this, so let's just look at what we get. First place, when we subtract these off, the c's will subtract off, we'll end up with no c. We'll have a times k squared minus ah squared, from which we can factor a. We get a times k squared minus h squared. And similarly, we'll have bk minus bh. We can factor out the b. We get b times k minus h, all divided by k minus h. And we wonder if maybe there's a way to divide k minus h into this expression. Of course, we can divide k minus h into this, but that doesn't do us much good unless we can divide it into the k squared minus h squared also. Foregoing any kind of superstitious foolishness, we factor k squared minus h squared into k minus h times k plus h. And then we see that we can easily divide the k minus h into the numerator. The k minus h divides here, leaving us a times k plus h. It also divides over here, leaving us b. So the slope is a times k plus h plus b. So there's an interesting exercise in setting up a slope and in doing a little bit of algebra to simplify the expression. We now move to a review of the linked outline in preparation for your test. Number 25 in the linked outline concerns the derivation of the slope equals slope equation. That is, we have a point x1, y1 and a point x2, y2 on a graph of a linear function. And we want to find the equation for that function. So to do that, we postulate a point xy and we write the conditions for xy to lie on the line. First, the slope between x1, y1 and x2, y2 we obtain by easily finding the run and the rise. The rise is y2 minus y1, run is x2 minus x1, so the slope is y2 minus y1 over x2 minus x1. That's a little small, you might not be able to read it. We then calculate the slope between either of the points and xy. In this case, we'll use x2, y2. It doesn't matter which one we use, we're going to get the same result ultimately, or it'll have at least the same effect. From x2, y2 to xy, the run is x minus x2, the rise is y minus y2. So we have a slope of y minus y2 over x minus x2. Again, that's written pretty small, you can't see that, but we've written them bigger here. So the slope here is y minus y2 over x minus x2, and that's equal to the slope here, y2 minus y1 over x2 minus x1. This can easily be solved for y to give us the slope-intercept form of the straight line through these 2 points. This is the slope equals slope form, and this is how we get it. Another way to get the equation of a straight line through 2 given points, x1, y1, and x2, y2, is simply to substitute the coordinates of those points into the form of the general linear function, y equals mx plus b. And we're going to get y1 equals mx1 plus b, y2 equals mx2 plus b. If we subtract these equations, b is going to subtract off, and we're going to have an equation that we can solve for m in terms of x1, x2, y1, and y2. Having obtained m, then we can plug that back into either of these equations and obtain an expression for b.